Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to learn the topics of sampling theory and linear regression analysis. In this module on linear regression analysis, we are going to continue on the topic of multiple linear regression analysis with R software. So, you can recall that in the earlier lecture, we had considered the estimation of vector of regression coefficient beta by the ordinary least square estimation, right. And after that we also stated the estimator of sigma square, but how to obtain that we will try to do in the further lectures. And after that we had seen how we can obtain the fitted model and how we can obtain the residuals as well as fitted values. So, before I go further with the estimation of sigma square and other and maximum likelihood estimation, etc., let me try to show you whatever we have done, that how those things can be executed in the R software. So, what I will try to do, I will try to take an example, and this is the same example that I discussed in the first lecture on multiple linear regression model, and I will try to fit a model. And in order to do it, I am going to use the same command that we discussed in the case of simple linear regression model. So, it is very important that before starting this lecture, you must have a quick review of the lecture in the case of simple linear regression model, where we had implemented the command LM in R software. Okay, so, believing that you have you had revised that lecture, let me begin this lecture now here. Okay, so, now this is the same data set where we have collected the information on 20 students about their marks denoted as Y, the number of hours of study in a week, these are denoted by here x1, and this data is given here, see here x1, and then number of assignments submitted per week, this variable is denoted by x2, and the number of hours of play per week, which is denoted by x3, and we have obtained here this data. So, this data goes like this, that for the student number 1, the student has got 180 marks out of 250, and the student had studied 34 hours in a week. The student has submitted 3 assignments in a month, and the student has played 15 hours in a week, and the same information for student 2, student 3 up to student 20. Okay, so, now first I try to explain you the command. Command is the same, but now you will see here there are some more options, but definitely we are not going to use that option, because this command here LM, which is used to fit the linear regression model, that is a very general command. And as I said that there are many more topics in case of linear regression modeling, but we are not going to cover here all the topics. So, I will restrict myself only to those options which I am going to use on the basis of the topics which we have covered in this course, right. So, here once again, just like the simple linear regression model, we use the command here LM, which is here like this, and then after this there are different options, which is here, one is here the formula, and another here is the data, and there are many other things, but I am not going to discuss those things, but let me explain you the formula and data, which are exactly the same what we had done in the case of simple linear regression model. So, this formula will give you will be helpful in providing the model specification to the R software. So, this formula is an object of the class formula, and this has to be denoted using the y tilde, say x1 plus x2 plus and so on. You remember that earlier in the case of simple linear regression model, you had used the notation y tilde x. Right. Simply the second option is data, which is an optional data frame where you can input the data, and if you do not want to use the data frame, then you can input the data from the external, means you can specify the data vectors in your R console, and then you try to use the LM command. Okay. So, now and once you obtain the outcome of an LM command, then you can exercise different types of option to retrieve information on different aspects. So, as I said, formula is going to be like this: a response variable, whatever is the name of the variable, and then this symbol which is on your keyboard, this is equivalent sign or tilde sign, and then you have the terms. Terms are your independent variable. So, you have to give it in the terms of say x1 plus x2 plus and so on, whatever are your variables, you have to just express all the variable with a plus sign. Okay. Now, in case if you want to have a model without intercept term, then one option is this: you try to write down here y is equal to x minus 1. So, you have to insert the factor -1 in your formula, or alternative is that you can write down 0 plus x also. That will indicate to the R that in this case the model which you are going to find is a model without intercept term, right. And yeah, one thing I can share with you that if there is no intercept term in the model, then obviously there is no intercept term so no beta 0 and so no b 0, but the form of the estimator for the slope parameter changes. Well, I have not considered those things here, but those things are there. Well, in case if you want to retrieve the information on coefficient, then you have to use the option coefficients, and if you want to obtain the residuals, you have to use the option here, the commands residual with LM command, and if you want to have fitted values, you can use the command fitted dot values, and this will give you the value of here y hat, this residual will give you the value of E, and coefficients will give you the value of beta hat, which was your here B, right. After this, there is another option here, ANOVA, which is analysis of variance. So, at this moment in this lecture I am not going to talk about it. This is related to the test of hypothesis, so which I will be doing later on when I start a discussion on the construction of test of hypothesis. But here I am trying to inform you that this command ANOVA, it is used to obtain the or extract the results on the analysis of variance of the given set of data, right. So, now let me take over this model. So, the model which we have written, I am considering here the model with intercept term. So, I can write down the model here, this y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and whatever are the observations which are given for x1 x2 x3, they are going to be satisfied for by the multiple linear regression model, and we have here 20 observations. Okay. So, now I am storing this the values on x1 x2 x3 in 3 data vectors x1 x2 x3, and can here y. You can see here these are very simple data vectors, and if I am not using the simple data vectors, then I can club all this y x1 x2 x3 in the framework of a data frame also. So, now you are comfortable in using the concept of data frame. So, you can see here that this is how here I had entered the data in my R console. Well, I will try to show you also here, but before going into the linear regression modeling, the first assumption we have to verify that whether the data has got a linear relationship or not. Now, you see the model is said to be linear when it is linear with respect to parameter, but our trouble is this: I want to judge it in a real life, and our problem here is this: earlier in the case of simple linear regression model, we have only one x and one y, so I could make here a plot, but now we have a situation here, we have here y and a group of variable x1 x2 x3, and they are just inside a box. So, you cannot see them what is happening. you simply have here the values of y. So, but what you want to check? You want to check that whether the relationship between y and all these variable x1, x2, x3 is linear or not. So, one possible way out is this: I can check whether the relationship between y and x1 is linear or not, the relationship between y and x2 is linear or not, and y and x3 is linear or not. Right, definitely I am not trying to check here whether there is a joint relationship. It is a difficult task to do it graphically, and well, if you can come up with some idea, that will be nice. But at this moment what we are assuming that whatever tools we have, we can draw only here a graph between two variables. So, I am taking here x1 and y. Yeah, another option is this: we can also make some 3-dimensional graph, but again that will be restricted only to 3 variables, not beyond that. So, what we try to come up as a solution, that if we try to test or check, and if we find that the relationship between y and with respect to each of the variable x1 and x2 and x3, this is linear, then we can conclude that the joint relationship between y and x1, x2, x3 is also linear, although there can be some interaction effects also, but I do not know how to take the observations on interaction. So, I have no option here except to believe on or to rely on this idea and try to do as much as I can. Right. So, that is the reason. So, now what we try to do, that we will try to make a scatter plot between y and each of these variables. So, basically we will have here 3 scatter plots. So, instead of going through the individual scatter plot, I can create a matrix of scatter plots. Right. So, the advantage will be that you can visualize all the scatter diagram in a single shot, in a single diagram, which is more informative, which is more convenient. So, in order to create a matrix scatter plot, in R we have a command here, pairs, P-A-I-R-S, and this command has to be used like this: pairs, and inside the parenthesis you have to first use the equivalent sign or tilde sign, and you have to give all the variables corresponding to which you want to create the matrix plot. So, I am trying to choose here y, x1, x2, x3. There are 4 variables. So, those 4 variables are expressed like this: y plus x1 plus x2 plus x3. And yeah, this option here is main. This is used only to give the title to the main graphic. So, I am giving here a name matrix scatter plot. And if you try to execute this on the R console, you will get here a picture like this one. So, now first we understand how to interpret. So, you can see here, here there is here a y, and then here there is a x1, then x2, then x3, and the same thing is also here y, x1, x2, and here x3. So, you can consider as if here is some x axis and here this is y axis. It is something like this, right. So, now you come to here first diagram. So, this is the diagram between y and y. So, which is of not interest. Now, if you come to this one, please try to watch the movement of my pen. So, if you come to here, let me put it here 1. If you come to block number 1, this is a plot between, this is equivalent to plot between y and x1, right. So, you can see here, possibly you can see here, well, there is a good linear trend, right, and it is not very difficult. Well, now then you come to block number 2 here. This is actually the plot between y and x2. You can see here it looks a little bit haphazard. I mean, some points are here, some points are here, some points are here, right. So, well, I can assume linear relationship, but I am not really confident. Okay, so let us move forward. Now, you come to the block number here 3. So, this is a plot between y and x3. You can see here, well, there is a reasonable linear plot. It is not that bad, right. So, Now, before I try to conclude, let me try to give you the interpretation of all other blocks also. Now, if you try to make here a diagonal, then this matrix plot is a symmetric. This means this here, if you look at the block number 1 and block number here 4, so this is the same thing. The only difference is that the x's, y and x are interchanged, that is all, right. So, that is the reason that, and then whatever you are looking here in the block number 5, this is same as block number 2 plot. You can see here only the direction is changed, means instead of using the command plot xy, I am using the command plot yx. And similarly, if you try to see here in the block number 6, this is the same as block number 3, because they are symmetric. This is symmetric, this is symmetric, right. Okay. Now, if you try to come here block number here, see here 7. So, what is this thing? This is a plot between, see here, x1 and x3, and if you come to here plot block number 8, this is a plot between x1 and x2, right. And if you come to here block number here 3, so this is a plot between, see here, x2 and x3. So, although it is not our interest in looking the relationship among x1, x2, x3, because at this moment we are primarily interested in the relationship of y with respect to x1, x2, x3, right. But still this these 3 plots in block number 7, 8, 9, they will try to give you an information about the independence of the explanatory variable, right. So, well, I am not discussing here, but looking at this graphic, that will give you a first hand information about the multicollinearity problem in the data. And after that, if you try to see here these these 2 graphics, they are again the same, only the exchange of axis over here. So, you can see here that this is the symmetric plot. So, essentially in a matrix scatter plot, you have to look only into the upper part of the diagram, which is this one, that is all. Either upper one or lower one also, means you have to choose only one thing, and all other information can be followed exactly. Now, if you try to see, if you try to look into the blocks number here 1, 2 and 3. So, what we can see here that the linear relationship between y and x1 and y and x3 is 100% clear. Between y and x2 we are not 100% sure, but we have no other options. So, because there can be an interaction effect also, there can be other problems also. So, but for a while we assume that okay, this is reasonably linear and we move forward. Then we will try to see whether we are getting a good model or not. If there is any problem, then we have to come back and then we have to modify our variable, we have to use some transformation of variable, and then we can move forward. Okay. So, you can see here this is the the same scatter plot which you have obtained, but now in a much bigger way. So, you can now have a look. I have given it because in the earlier one I had made lots of this marks. So, I am reproducing it here again once again for you. So, that now you can look at this graphic and you can see what you can really infer for different type of relationship. Okay. So, now this is the scatter diagram, so that you can be confident that I have reproduced the same thing which you will obtain. Okay. Now, there is another option to check this relationship. And if you remember, in the beginning of the lecture, we had used the option correlation plot, and I had explained you in detail when I introduced some basic concept about the R software, that how to construct the correlation plot. So, I will not go into that detail, but I will. But if you have forgotten it, I will say that go back to your earlier lectures and try to see how you had obtained, how you had interpreted the correlation plot, and now I will try to make this plot in the context of our data. So, just for a quick review, so this correlation plot is obtained by the command cor plot, which is used for the visualization of the correlation matrix, right. So, the main thing is this main commands which we had used earlier and we will use here again. These are the main command is core plot, and then there are different options which is here core is the matrix or the correlation matrix that you have to give which you want to plot. Then you have to give the method, means the correlation structure and the degree of correlation coefficient is going to be indicated by a circle, by a square, by an ellipse, or by a number, or by some shade or color or pie diagram. And similarly, you have one more option here, type. Type is to show whether you want a full matrix or a lower diagonal matrix or an upper diagonal matrix using the command full, lower and upper respectively. Similarly, if you want to change the color, you have the command COL and so on if you want to give the title, etc. So, there are many commands. I will request you to go to help menu and see all the things, but here my objective is to create a plot for the given set of data. So, as we discussed earlier in the lecture, in order to construct this correlation plot, you need to install a package core plot. So, we install the package core plot using this command install.packages, and then we load it using the command library. Now, in this correlation plot, the data has to be entered into the framework of a data frame. So, what I try to do, I have got here a get a set of 4 variables y, x1, x2, x3. So, I try to create a data frame here and I give the name as x1, 2, 3, y. So, that you can remember it is x1, x2, x3 and y, right. And then this data frame has to be converted into a correlation matrix. So, before I go further, let me explain you what is a correlation matrix. Right. Suppose if I say I have got here 2 variables, say x and say here x1 and x2, suppose, then the correlation coefficient between x1 and x2, let me denote it by here, are x1, x2, right. So, now suppose I have got here 3 variables x1, x2 and x3, and suppose I want to create a correlation matrix. So, the correlation matrix of this x1, x2, x3 will be a matrix like this. The first element will be the correlation between x1 and x1. So, you can write down actually here, that is more easy to understand, x1, x2, x3, x1, x2, x3. So, the first entry will be the correlation coefficient between x1 and x1, which is equal to here 1. So, and similarly the second diagonal element will be r x2, x2, that is the correlation coefficient between x2 and x2, which is 1. And the third diagonal will be the correlation coefficient between x3 and x3, which will again be equal to 1. Right. Now, if you come to this other element, suppose here if you try to see, so this is the correlation coefficient between x1 and x2, and the next element will be correlation coefficient between x1 and x3. Similarly, here is the column which is going to be a symmetric matrix, because the correlation coefficient between x1 and x2 is the same as the correlation coefficient between x2 and x1. So, I can write down here correlation between x2 and x1, and similarly the third row first element will be correlation coefficient x3 and x1. So, x3 is coming from here and x1 is coming from here, you can see. Similarly, here the last element in the second row will be the correlation coefficient between x2 and x3, and similarly here in the third row and second column, this will become here r x3, x2, right. So, you can see here now this correlation matrix is going to be a matrix where all the correlation coefficient are presented together, and all the values of correlation coefficient will be lying between 0 and 1. Now, we are trying to create a matrix plot of this correlation coefficient values from this matrix, and we try to make it more beautiful, more informative. For that we use different types of option. Okay, so first I try to create here my correlation matrix. The correlation matrix can be created using the same command COR. So, if you try to give here a scalar, it will give you scalar value, but if you try to give here a say this data frame, then it will give you a matrix value. Okay, so I try to first I try to create this correlation matrix and I store it under x123y underscore COR. So, means you can imagine that you can remember that this is the matrix of x1, x2, x3 and y for correlation coefficient. Okay, now the correlation plot is created by the command cor plot CORRPLOT. First you have to give the name of the correlation matrix, remember, not the data frame. So, you try to give it a correlation matrix and then you have to give here the method number or whatever you want to choose. I will try to take different options. Now, if you try to see, this is how you are going to obtain. First I try to create the data frame of y x1, x2, x3 and then I try to create the correlation matrix, and this correlation matrix will look like this. So, you can see here, this is your here the correlation coefficient between y and y, this is the diagonal elements correlation coefficient between x1 and x1 and similarly for x2 and x3 here. Now, if you try to look on the non-diagonal elements, so obviously the diagonal elements are always going to be 1 and we are not interested in those things because these are obvious values. The more important values are on the off diagonal parts, and if you try to look at the first value, I am trying to use here different colors of pen. So, this is here 0.8779040, this is the value of the correlation coefficient between y and x1. And this is the same value if you try to see here in the first column, second row, this is the same value, this is the same value, but this is the correlation coefficient between x1 and y, but that does not make any difference, they are the same value. Similarly, if you try to go for other values, for example, if you try to look at this value, this is the correlation coefficient between y and x2, and similarly here in the first column, this is the value here of correlation coefficient between x2 and y, right. So, they are again the same values, and similarly if you try to go for the third value here, this value is the correlation coefficient between y and x3, and this is the same value here, correlation coefficient between but x3 and y, right. So, these are the values of interest, and similarly you can see here these values here which are here like this, they are the here like this, they are the correlation coefficient, but they are the correlation coefficient between x1, x2, x3 and so on. But since they are not our interest, so we are not going into those details, but you can see here that here in this case possibly the values are quite small, but in other cases there is some correlation, but that is going to happen in most of the real life situation, particularly when you are trying to deal in the data sciences where there are millions and billions of observations. So, that is what we have to learn, that how you are going to interpret and look into the data. Now, the outcome of this matrix plot will look like this, you can see here. So, on the diagonal elements we have here the values, and you can see here now try to observe on two things. One is the value and other is the shade of the color. You can see here the value is 0.24, but the color is quite low, right. The color is not dark as compared to this value here 0.88. 0.88 you see the value is also high and the shade of the color is also darker. So, now what is the meaning? The shade of the color is going to indicate the degree of the correlation. So, you can see here these values, and you can see here they have got the different shades. It is not like that in the recording you are looking at these shades and they are looking to be faded. No, degree of shade is proportional to the magnitude of the number. So, lower the number, lower the shade, higher the number, darker the shade, and this scale is also given here, you can see. Right. So, this is your correlation matrix plot. For example, this 0.88, it is trying to give you the correlation coefficient between y and x1. This is trying to give you the correlation coefficient between y and x2, and 0.81 is the correlation coefficient between y and x3 and so on. Right. So, this is how you can, by looking at this picture at a glance, you can very easily see what is the nature of degree of correlation coefficient and the degree of linear relationship, and this is going to give you much better information in terms of shade of the color as well as magnitude, both are embedded together, right. And this is the screenshot of the same outcome. Okay, now means other option is this, instead of using the option method equal to number, I can use here method equal to shade. So in this case you can see here that the degree of shade is proportional to the degree of correlation, but here you will not get the magnitude of the correlation coefficient. So I can make here a very simple rule that the degree of correlation coefficient is proportional to the degree of shade of the color, right. For example, you can see here on the diagonal element it is the darkest, because the correlation coefficient is always 1. So that is the maximum value. But you can see, if you try to look over here, compare block number here 1, block number here 2 and block number here 3. You can see here that the degree of shade is changing. So the correlation coefficient in the block 1 is the lowest, then followed by the correlation coefficient in the block number 2, and then the block number 3 has the say highest correlation coefficient among this block number 1, 2 and 3. Right. Similarly, if you try to take here, say this another option here, method equal to ellipse. So in this case, what is happening? Those numbers are replaced by, or those squares are replaced by the form of an ellipse. So if you want to understand it, you can first look into the diagonal elements. So the diagonal elements, you have got here a simple line. What does this mean? If you try to take here an ellipse and try to press it from the upper and lower side by your hand, then it is something like this. You take a ball in your hand, something like this, and try to push from both the sides like this. So what will happen? Suppose I have here sort of here ball, and I am trying to put my hands here and I am trying to press it. So what will happen? This ball will become flatter. It will look like an ellipse, and if you try to push more force, or if you try to push the ball with more force, it will become practically flat. So that is the maximum what you can achieve by pressing the ball. This is the same thing which is indicated in this slide also. Okay, so this is what is indicating here, that and this width of the slide is indicating the correlation coefficient. So on the diagonal element the correlation coefficient is 1. So the width is going to be nearly very small. So the rule is this width of the ellipse, that is inversely proportional to the correlation coefficient. Higher the value of correlation coefficient, that means the width is going to be lower. So in this case, if you try to look into figure number 1, 2 and 3 here, you can see here 1 has the maximum width, so the correlation coefficient is lowest, and then this second one, block number 2, this has got some width, and this block number 3 has got this width. So you can see here block number 3 has got the lowest width among this 1, 2 and 3. So the correlation coefficient of this one is going to be the lowest, and the correlation coefficient of this one is going to be the highest among block number 1, 2 and 3. And the shade also, you can see here the shade is the, if you try to see a shade here, shade here. So you can see here the shade is lighter than block number 2 and block number 3. So if your magnitude is less, then your shade is also lighter. So by looking at the width of the ellipse and the shade of the ellipse, color of the ellipse, you can have a fair idea that how the correlations are present in the variable x1, x2, x3. So now we are confident that okay, we take a call that okay, our relationship between y and x1, x2, x3 is approximately linear, and we will try to go with the linear model. So in order to fit this model, yi is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 plus beta 3 xi3 plus epsilon I based on 20 observation, we are going to use the same command that we use in the case of simple linear regression model, but I am trying to extend it. So the command is the same here. Earlier you had written lm y tilde x, now I am writing it here y, and now my independent variables are x1, x2, x3. So I am trying to write all the variables which are joined by the plus sign, right. So, I am writing x1 plus x2 plus x3 and this equivalent or tilde sign. So, this is going to indicate that y is to be regressed on x1, x2 and x3, right. So, now if you try to execute it, you get here this type of outcome. So, you can see here what are you getting here. The first value here is intercept term. So, it is trying to give you the value of beta 0 hat, which is you are indicating by b 0. The value corresponding to variable x1, it is 1.997. This is the value of beta 1 hat, which you are indicating by b 1. So, and then the value corresponding to x2 is 3.918, which is the value of here beta hat 2, which is here indicated by b 2. And x3 has a value 6.106, which is the value of beta hat 3, which you are trying to indicate by b 3. So, what is happening here? You had the coefficient vector beta as beta 0, beta 1, beta 2 and beta 3, and these values have been obtained by the ordinary least square estimate b, whose values are given by b 0, b 1, b 2 and b 3, right. So, now based on that your fitted model will become y is equal to, okay. So, now the fitted model is y is equal to this b 0 coming from here plus b 1 coming from here x 1 plus b 2 coming from here x 2 plus b 3 x 3. So, this is our fitted model, which you can obtain from the this outcome, right. So, this is exactly what I have rewritten here, that your ordinary least square estimator is given by like this. So, now these are the values of b 0, b 1, b 2, b 3, which you have obtained here like this. So, now at least I have finished my first part, that looking at this outcome, you know that how these values have been obtained. They are obtained using this expression. And what are these values? These are these values, which are the estimated values for b 0, b 1, b 2 and b 3. So, now you understand at least what is happening inside this R software, and this is the screenshot what I did. And after this, exactly going on the same line as we did in the case of simple linear regression model, we will try to find out the fitted values as well as residuals. So, the fitted values can be obtained by here the expression y hat equal to x b. So, in case of multiple linear regression model, you have to use the same command, that fitted dot values, and inside the parenthesis earlier we had used lm y tilde x. Now, I am using here the new object y tilde x1 plus x2 plus x3, and if you try to do it here, you have this outcome. So, you can see here the first value, it is the value of y1 hat, which is 180.0045. Second value here is the value of y2 hat, and similarly here this 20th value is the value of y28 hat, right. So, you can see here that it is very easy to obtain the fitted values even in the case of multiple linear regression model. And now, you can compare these fitted values from your observed values of y. So, it is something like this. If you try to use the values of x1, x2, x3 for the first set of observation in the fitted model, then you will obtain the value of y as here like this, which is y1 hat. And similarly, if you try to use the second set of observation on x1, x2, x3, and if you try to substitute those values in the fitted model, you will get here the value 116.0273, which is y2 hat, and so on, right. Okay, and this is the screenshot of the same outcome. And now, I try to find out the residual vector. So, you can see here now in this case E is a vector E1, E2, here he 20, because we have 20 observation. So, now here this y, which is here observed, and y hat here is fitted, and if you try to take the difference, you will get this value. So, now in order to obtain the residual vectors, we have to use the command residuals. and then inside the parenthesis you have to use the same object lm y tilde x1 plus x2 plus x3, and you will get here this type of outcome. So, you can see here we have the similar thing. The first value here is the value of E1, that is the first residual, second value is the second residual, third value is the third residual, and the last value 20 here is the last residuals. So, the first residual is y1 minus y1 hat, and E2 here is by y2 minus y2 hat, and so on. Right. So, you can see here it is not difficult to obtain these residuals. Right. So, let me first try to show you all these things on the R console also, and this is here the screenshot. So, you can see here I already have entered the value here y of y x1, x2 and x3. So, first I try to create here the matrix scatter plot. You can see here this comes out to be like this. So, this is the same screen plot which you have obtained. Right. Now, after this, if you want to create this correlation plot, so I will use the first command here, that first you have to create the data frame. So, I try to create here the data frame, you can see. So, you can see here this is your data frame, right, same data set which you had obtained. Now, you try to find out the correlation matrix of this data set. So, I clear the screen, it will be here like this. So, this the outcome will here look like this, you can see here. Then after this I would like to create the correlation plot. So, I already have installed this package corplot on my computer. So, you can see here this is loaded, and now if you try to use here the command for this here corplot for the number, you can see here you get here this outcome. You can see here now very clearly that how the shades are changing, and if you want to use here the method equal to here shade, so you have to simply use this command on the R console. You can see here you are getting here the shade, right. And similarly, if you want to have here ellipse, so what you have to do, you simply have to give here command here ellipse, right. So, this is the same outcome which I shown you on the slides, and after that if you want to fit here a model, so you can see here this fitting can be using the command lm. You can see here this is the same outcome which you have obtained here, right, just by writing the command lm y tilde x1 plus x2 plus x3. And if you want to retrieve the coefficients from this outcome, you simply have to use the command coefficients, and you will get here only the value of the coefficient. And similarly, if you want to obtain the fitted values of this output, then you have to simply use the command fitted dot values, and inside the parenthesis the object lm. You can see here you have got these many values. Well, if I try to make this slide bigger, and if I try to just show you once again, you can see here this is like this. So, there are 20 values which are trying to give me the values of y1 hat, y2 hat up to y20 hat, and now if you want to find out the residuals, you can see here you can use the command residuals, and inside the parenthesis you have to write the lm object or the formula which you have used for fitting the model, and you will see here you can get here the. So, you can see here it is not difficult at all, right. So, now you have seen that it is not difficult at all to find out those values which you have obtained in theory on the basis of a data set inside the R software. I am sure that this will remove the fear from your heart that sometime because of matrix theory and other things, people may think that the things are very complicated, but they are not. using them is very simple, straightforward, but the main challenge is how to interpret the value. This is something like this. When a doctor looks in the X-ray or an MRI or an ECG, based on that the person has to determine whether his patient is healthy or not, or if there is any problem or not. Right. Now, if somebody knows only to look into the ECG or this X-ray report, but if the doctor does not understand what is happening correspondingly inside the body, do you think that will you go to the doctor once again who don't know by looking at the X-ray that what has happened inside the body? I am sure you will not go to that doctor anymore. Same thing is with the statistician also, or as a data scientist also. If you just know how to interpret the data, but you don't understand what is happening behind the data, what is happening inside the data, you cannot be a data scientist. You will simply be a compounder. So decide what you want to be now. If you practice, if you learn the software outcome, if you learn the theoretical construction, I am not asking you to have the proofs always, but you have to understand the construction, how the tools have been constructed, and whatever is the software outcome, what are the values which are being computed in the software outcome. That is my experience. Your experience may be different, but in my opinion it is not possible to become a good statistician or a good data scientist without having a one-to-one correspondence between the outcome of the software and the theoretical construct or the basic concept behind that value. So, you try to take some simple examples, just try to take a data set of 5 values, 10 values, try to create it yourself and try to see whatever issue you are trying to create inside the data, is this getting reflected in your model? You can take a data by just creating yourself where the curve is non-linear, and then try to fit a linear regression model and see what happens. Well, in the next lectures I will be going more into the details, and then all other aspects will come into picture. So, till then you practice, and I will see you in the next week. Goodbye.